Welcome back. Please see the previous video for an introduction, but just know that this video is most likely going to be taken up entirely with reading part 2 and maybe part 3 of the manual. So I'll just get started so I don't waste more time. Environment Control and Life Support System, ECLSS. The ECLSS maintains the spacecraft's thermal stability and provides a pressurized, habitable environment for crew and onboard avionics. The ECLSS also manages the storage and disposal of water and crew waste. ECLSS is functionally divided into three systems. The pressure control system, which maintains the crew compartment at 103 kPa with a breathable mixture of oxygen and nitrogen. Nitrogen is also used to pressurize the supply and wastewater tanks. Atmospheric revitalization system, which uses air circulation and water coolant loops to remove heat, control humidity, and clean and purify cabin air. Active thermal control system, not implemented, which consists of two Freon loops that collect waste heat from orbiter systems and transfer the heat overboard, either through radiators or ammonia boilers. As Dragonfly has not yet been equipped with active thermal control systems, most heating and cooling operations are done by passive control systems, whereas super-cold cryogenic reactants are heated prior to entering the FC stack, thus cooling the electrical equipment. The same is done with wastewater, which is circulated throughout the vessel. As the water in the wastewater tank overheats, any boiling excess will be vented through the two non-propulsive vent valves. The only unbalanced thermal reaction is that of the fuel cell, which, in the absence of active cooling equipment, will overheat within 5 to 8 hours. The only cooling possibility for a fuel cell is either shutting down, or alternatively using fuel cells 1 and 2, or purging. Pressure control system. The pressure control system normally pressurizes the crew cabin to 103 plus or minus 10 kPa. It maintains the cabin at an average 70% nitrogen, 27 kilograms, and 30% oxygen, 9 kilograms. Mixture that closely resembles the atmosphere at sea level on Earth. The system also provides cabin atmosphere necessary to cool cabin air-cooled equipment. Oxygen partial pressure is maintained automatically between 20 and 23 kPa, with sufficient nitrogen pressure of 78.3 kPa added to achieve a total cabin pressure of 103 plus or minus 10 kPa. Positive and negative pressure relief valves protect the structural integrity of the cabin from overpressurization and underpressurization respectively. The pressure control system nitrogen is also used to pressurize the supply and wastewater tanks. Nitrogen is stored in two identical 3-liter tanks serviced at a temperature of 288 Kelvin that contain up to 20 kilograms of nitrogen each. The provided nitrogen is enough to repressurize the cabin and docking hatch for up to 6 docking hatch repressurizations for EVA. The two N2 Tank 1 and N2 Tank 2 switches, located on panel O1, or the main ECLSS panel, control isolation valves to each of the two nitrogen tanks. When closed, nitrogen from the tank is not provided to either pressure control system or as a pressurizer for the wastewater cooling loop. A second set of ISO valves control N2 flow from the tanks to the pressure control system. Note that N2 will continue to pressurize the wastewater tank even with both of the ISO tanks closed if any of the N2 tank valves are open. The N2 supply switch will close N2 from the pressure control system to be vented into the cabin through the N2 from the tanks, though the N2 from the tanks might continue to flow, either as a pressurizer for the wastewater tanks or to the overpressure vent valves. Nitrogen pressure is regulated at the N2 supply valve with a nominal pressure of 78 to 80 kPa. The crossfeed switch must be in its open position for tank 2 to provide nitrogen pressure to the cabin. During normal operations, only N2 Tank 1 will be used for the cabin pressurization and N2 Tank 2 for wastewater cooling loop pressurization. A set of two, one for each tank, high-capacity nitrogen overboard dump valves will quickly discharge overpressurized nitrogen from the N2 pressure control system. Though the N2 tanks have no heaters to raise tank pressure, it is possible for excess heat from the wastewater cooling loop to transfer to the nitrogen, thus overheating and overpressurizing the N2 tanks. To avoid damaging the tanks, the two valves can be used to quickly discharge the overheated nitrogen and bring the tank pressure back to a safer value. Oxygen from the power reactant storage and distribution system, or the cryogenic oxygen supply system, is routed to the pressure control oxygen system, first to a pressure regulator, O2R1, that reduces oxygen pressure to a lower 280-290 kPa. At this pressure, an electrical boiling plate, BLR, can transform the cryogenic oxygen to its gaseous form by heating it to a surface temperature of 295 Kelvin. The pressure gas from the boiler plate is then passed through a second pressure regulator, O2R2, that releases oxygen in the O2 pressure control system at 23 to 25 kPa and at an ambient temperature of 22 degrees Celsius. The same O2 supply valve as from the N2 controls O2 discharge into the cabin circuit. Note that the boilerplate heats oxygen from cryogenic to room temperature is powered not by the battery because of the rather large power consumption of the boiling plate. Instead, DC-1 is used. Without DC power on the DC-1 bus, the boiling plate will not be functional and no gaseous oxygen can be produced. Monitor the R1 temp R2 indicators to get a readout of the boiling plate functionality. Temperature for the R1 regulator, usually around serviced 170 Kelvin, is the temperature directly from the cryo-O2 pressure manifold. Temperature of the second pressure regulator must be around 295 Kelvin, at which at the service pressure of 1 atmosphere renders the oxygen to its gaseous form. If the two temperatures are identical, the boiler plate is either unpowered, has been shut down, or is damaged. At the cryogenic temperature of 170 Kelvin, oxygen will remain in its liquid form and will not be discarded into the cabin atmosphere. Monitor the O2 flow indicator to get a reading of the amount of oxygen passing through the oxygen revitalization system. Atmosphere revitalization system. Two electrical fans provide continuous air circulation needed in the cabin. Air from the cabin is directed into an air revitalization circuit, whereas CO2 is removed by lithium or LiOH containers, and humidity is controlled by a DC-powered humidity separator. Both fans function on an independent bus, DC fan, that can be connected to either DC-1 or DC-2 main buses, or directly from the battery. From the LiOH and humidity, Hum-SP, the air piping then interleaves with cryogenic H2 passing from the H2 cryotanks from the to FC1, thus cooling the air to a lower 22 to 25 Celsius before returning it to the cabin. Before actually reaching the cabin, the air is mixed with oxygen provided by the R2 regulator, bringing fresh oxygen from the PRSD supply, if the R2 pressure valve switch is open. Most of the cabin air properties can be monitored on the top panels the top indicators on panel O1. O2 partial pressure, N2 partial pressure, CO2 partial pressure, and the total ambient pressure. Left indicators show the cabin atmosphere status, whereas right indicators show docking hatch atmosphere status. Ambient temperature can also be monitored on this part of the panel. Ambient delta pressure, delta temperature can also be monitored to indicate eventual cabin leaks or depressurizations. A third indicator monitors the pressure difference between cabin air and atmospheric revitalization system. A zero delta pressure indicates an improper functioning of the two circulating fans and that the air is not circulated. And then we have more checklists. How long have I gone? I've got plenty of time. Communications is blank, as you can see. It's just a blank white page. Radar and docking system. And I guess I'll read it. These next parts aren't exactly required, which means I probably shouldn't read it. The vicinity awareness system right here, I'll just go through this really quick. One of them shows the craft from above, I believe it's the left, and the other one shows the craft from the side. So using these two, you can see, or you can visualize a three-dimensional image of where the craft is in relation to nearby objects. So in this case, you can see the craft in the center and two objects in front. Both are slightly below. And it has about a range of about 100, or incremental range up to 500 meters. You can move the antennas, supposedly. I haven't gotten it to work, actually. The reaction control system, or ICS, is very similar to all the other reaction control systems, except for I don't see it. I will talk about it then when I get there, and how I've never actually gotten it to work. Oh, here we go. The CG balance offset. So when you dock with something, um, here's a image of the Dragonfly. Here, I'll just scroll back up to the top. So when you dock with something, then the extra mass of this throws the RCS system off. So it should compensate so that when you, say, want to rotate upward, it changes the amount of flow coming through each of the RCS ports so that you only rotate and not translate. I haven't actually gotten it to work yet, and you will see that when I fly the Dragonfly in a bit. Next video, actually. And the AD eyeball just shows you position of the ship, and the orientation in relation to um, various reference frames, which is handy. And that is it. I will fly the orbiter in the next video. Sorry for this video being so short, but I guess it makes up for the other one being so long. Sorry for both of these videos being so boring. And I will see you next time.